Yeah. All right, so we're happy to have Li Hu give the IQS seminar this week. So Li Hu comes to us from China. He studied at Sun Yat-sen University, studying chemistry, and then he did his Bachelor's of Science in the U.S. in Michigan, Ann Arbor. And then he came to Rochester, where he's working his PhD with us. So happy to have you here, Li Hu, give your talk remotely. So the theme that Li Hu's been very interested in foundational questions in quantum physics, and we'll be talking about control and simulation of quantum systems. So over to you.
Okay. Okay. Hello, everyone. My name is Li Hu, and I'm currently a sixth-year grad student in the University of Rochester. And today, my topic is on quantum state driving, wave function collapse, and open quantum system dynamics. So the talk is based on a theories paper published with my advisor, Andrew Jordan. So in today's talk, I will talk about three different topics. So the first is that how to drive a quantum state to evolve along a design trajectory. Then we will show how the above results can be used to describe the collapse of the wave function. And finally, we will show what happens when we generalize the above driving techniques into the non-unitary regime. We obtain a new formulation of open quantum system dynamics that has probabilistic unitary interpretation. So for the first part, we focus on the quantum state driving. So in this section, we will ask these questions. For a given quantum trajectory psi t, how can we find in Hamiltonian to drive a quantum state to evolve along the trajectory time optimally? So here we assume that we know the full history of psi t beforehand, and we assume that we can apply any control Hamiltonian ht as we wanted, except that the energy variance of the Hamiltonian is bounded, which basically means that we only have limited energy resources. So to solve this problem, one thing we can do is that we can cut the trajectories into many infinitesimal pieces. And then if we can find a Hamiltonian that can drive between those infinitesimal pieces, and then we apply such Hamiltonian to each of the pieces, then hopefully we can drive the quantum state to travel through the trajectories, right? So it turns out that this problem is related to the quantum Braxton problem, which asks that given two quantum states psi I and psi f, what is the Hamiltonian ht that can drive the transition from psi I to psi f in minimum time? And this problem has been solved in Kaleni et al. In 2006. They assume that with limited energy variance, which is bounded by some value, say omega squared, they solved for the optimal Hamiltonian, which is a time-independent Hamiltonian, given by this formula. They've also solved for the minimum time t. So to better understand what exactly this Hamiltonian is doing, here I have a cartoon, which on this block sphere, we have the psi I, psi f, and the psi f prime. So the psi f prime is constructed by the Grant-Schmidt process from psi f to psi I, such that the psi I is orthogonal to psi f prime. Then, to time optimally drive psi I to psi f, we only need to drive the quantum state along the gray circle formed by psi I, psi f, and psi f prime. So once we know how we can make use of a time-independent Hamiltonian to drive between two fixed quantum states, we can basically apply this time-independent Hamiltonian to those infinitesimal points. What we will do is that we plug in the psi t into the psi I part, and psi t plus delta t to the psi f part, and then we obtain this infinitesimal version of the Hamiltonian. Next, we rewrite the psi prime t plus delta t in terms of psi t and the first and second time derivative of psi t using Taylor series, and also make use of the Grant-Schmidt constructed vector, we can obtain this driving Hamiltonian. So basically with this driving Hamiltonian, we can drive any quantum state through any design trajectories. Here, the psi tilde differs from the original sign by a phase factor. So this phase factor is used to cancel out the open path Barrett's phase. And here, the phi dot term is used to make sure that the psi t has correct global U1 phase. So in cases if you don't care about the global phase, then you can just drop these terms. We can also generalize to of the results to the mixed state case, which produce this Hamiltonian. And here, the psi I is the instantaneous eigenstate of rho t. So in the section 2 and 3, we will show that how those results can be useful in wave function collapse and open quantum system. Okay. Once we obtained the explicit expression for the Hamiltonian, we can solve for things like its mean energy and energy variance. And then we can solve for the cases that if we have limited resources, which basically means that the energy variance of the Hamiltonian is bounded by some maximum value, then only the trajectories satisfying this condition is drivable, which basically gives the quantum speed limit of the evolution of psi t. So basically the expression here states that with limited resources, only the trajectories like this is drivable. Okay. So this is the first part. So in the second part, we will focus on the wave function collapse. And we know that there are a lot of different interpretations of quantum mechanics, right? Like the whole Copenhagen interpretation, the Many-Worlds interpretation, the decoherence theory, the Bohemian mechanics, the cubism, and so many more. Then it is curious to ask that is there a theory that is fully compatible with standard quantum mechanics, yet capable of describing the dynamics of wave function collapse? And in the following, we will show that by making use of the aforementioned result, we can come up with a formalism that is fully compatible with standard quantum mechanics, yet is capable of describing the dynamics of wave function collapse. Okay. So the motivation is this. During the measurement process, the atoms and the molecules in the measurement devices interact with the probed quantum objects, right? And since such interaction is governed by the Schrödinger equation, the collapse dynamics should also be governed by the Schrödinger equations. And therefore, we should be able to, in principle, reconstruct an effective measuring Hamiltonian responsible for the collapse dynamics. And here we take the following assumptions. First, we assume that the wave function collapse is not an instantaneous process. Instead, it takes some finite non-zero time to complete. Okay. In this assumption, we can come up with such equation of motion, basically describe how the density matrices evolve infinitesimally in terms of time. Okay. So the denominator term is a normalization factor. So basically we can just ignore it. And the U-term come up with like two terms. The first term is the contribution from the system, which contains the Hamiltonian of system. And the second term is the contribution from the measurement. The next assumptions we made is that since the wave function collapse is an extremely fast process, the contribution from the measurement dominates, and we can basically take the system Hamiltonian to be zero over the measurement processes. Okay. So this assumption would allow us to simplify further of the evolution dynamics and replace the U to just N, and the story will just be simpler. Okay. Now we will try to see how we can describe its dynamics. And we start with pure initial states because it's simpler. In this case, we consider the simpler case where the rho 0, which is initially pure. Then, during the process of projective measurement, the density matrices rho t should not become more mixed, since information is being constantly extracted from the system. Okay, if rho t is not becoming more mixed, then we can see that if initially rho 0 is pure, then at any later time, rho t would remain pure, right? Which means that what we essentially have is unitary dynamics, right? It's pure all of the times. And then the idea is that we can focus on a specific collapse trajectories. And from these specific collapse trajectories, we can try to reconstruct a measuring Hamiltonian responsible for these specific collapse trajectories by making use of the driving Hamiltonian we just derived. And here are the steps to reconstruct the measuring Hamiltonian. First, we assume that the process to be time continuous, and we can calculate theoretically or measure experimentally how the quantum state psi I changes infinitesimally to psi t plus delta t. We can basically make use of the aforementioned formula to write down this equation. The denominator is normalization factor, so it doesn't really matter. What really matters is the nominator part. So what the equation really says is that there exists a measurement operator such that the m would take psi t to psi t plus delta t. Next, we try to calculate the time derivative of psi using its limit definition, or we can approximate with experimental data. And finally, we make use of the Hamiltonian to reconstruct the measuring Hamiltonian. Okay, so let's see example. In this example, we consider the measurement on a two-level system. Let's consider a general state, which initially is indexed by A0, 0 plus B0, 1, such that the psi 0 is normalized. And here we borrow the measuring operator from the weak measurement and condition measurement to take the m to be this form. So the R here is a stochastic readout from continuous measurement, is from minus infinity to plus infinity. And the sigma z here denotes the basis we are measuring. And 1 over tau here is the measuring strength. So the larger the measuring strength, there is more closer to a projective measurement. And the stochastic readout RT would be conditional on the current state rho t on this formula. So, and by the aforementioned method, we can solve for the Hamiltonian, okay, which is given by this formula. So to better understand what exactly this Hamiltonian is doing, we have this cartoon. So here, the vector here is the block vector of the Hamiltonian. And the dot here denotes the current state of the density matrices. And we can see that the VH, the block vector of the Hamiltonian, is always orthogonal to the block vector of the density matrices. So what's happening is this. When we are measuring the quantum state, we will get a series of readout RT, right? And then the quantum state V rho will move stochastically either up or down along this arc according to the RT. And there are two stabilization points, the 1 and 0, which is the eigenstate of sigma z. And we will find that if the quantum state evolves to 1 or 0, then such measuring Hamiltonian will vanish, which basically means that effectively there's no Hamiltonian acting on the quantum state at that moment. Also, this plot illustrates why we cannot simultaneously measure the quantum state along two non-commuting bases. Because if we do so, we will have two different block vector for Hamiltonian, like V1, VH1 and VH2, right? And the quantum state will evolve around those two different axes in chaotic ways. And there will be no longer be stabilization points like 1 and 0 anymore. Okay. And then we can also calculate the energy variance of the imaginary Hamiltonian, which is given by the formula here. And we can see that the stronger the measuring strength, which is 1 over tau, the larger the energy variance. And also, the larger the readout RT, the larger the energy variance. And if A or B equals 0, which means that if we reach the 1 or 0 on the Bloch sphere, then the energy variance vanishes. Okay, so now we understand how such Hamiltonian works, like the imaginary Hamiltonian works. We can come up with some experimental verification plans. We can first prepare a non-initial state, which is psi 0 equals to n hat. So here, n hat here denotes the direction, the vector on the Bloch sphere. And then we can make a weak measurement with the stochastic readout RT. Then we can apply a counter measuring Hamiltonian minus HT to push back the qubit to where it was used to be, which is given by the formula here. And then we wait for a time period of t such that the contribution from the system's own Hamiltonian vanishes, which basically means that the unitary operators here equals the identity. And finally, we measure the qubit in the basis n and calculate the probability that the result is n. Okay. After counting for effects like noise and errors, and if we can show so that we have almost 100% probability that the result is n, then it basically means that our counter measuring Hamiltonian really works, which means that the measuring Hamiltonian is indeed the effective Hamiltonian responsible for the wave function collapse processes. So this experimental scheme has a name called kicked quantum non-dilution measurement. Okay. We can also generalize our result to n-level system. We can assume a general n-level initial state and calculate the Hamiltonian. And well, the result here is less useful because of its complexity, so I will not go into details. We can also consider the measurement on a simple harmonic oscillator. We assume a ground state of simple harmonic oscillator, and we measure it on the position. And we can calculate for its Hamiltonian and also energy variance. But in these cases, the Hamiltonian is non-local, so which is open to further interpretation and discussions. So the above is for the pure parts. For mixed initial states, we are divided into two parts, the proper mixture and the improper mixtures. For proper mixtures, the density matrices can be decomposed in its instantaneous eigenstates with such a probability, pi. And such decomposition can be interpreted as a classical mixtures of pure states. And then, for each specific state being measured in the ensemble, we can say that there's probability pi that the measuring Hamiltonian is given by h, which is dependent on the initial state, psi I. And such Hamiltonian is unknown to us because we don't know what the initial state is. Once we have accumulated a series of reals RT, we can Bayesian update our estimate of pi, which indicates a process of purification. For improper mixtures are the result from the partial tracing of a larger pure quantum state, for example, like this. Well, in these cases, we can still argue the same way as we did for proper mixtures, since proper and improper mixtures are physically indistinguishable from each other. Or alternatively, we can obtain the measurement Hamiltonian by letting the measurement operator to be m total, which is equal to the m a o times ib x on rho ab. The measurement Hamiltonian obtained in this way will be non-local too, so it's up to further interpretation. So this, yes, questions? Okay, so this is what we have for wave function collapse part, and in the next we will discuss open quantum system dynamics. And let me first briefly introduce what is open quantum system dynamics. We know well that if we have a closed quantum system, then we can describe its evolution dynamics well by the Schrödinger equation, right? But in practice, there's no perfect isolated system. All of systems are surrounded by its environment. And so there will be an inevitable interaction between the system and the environment. And when such interaction is significant, the system can no longer be described by the Schrödinger equation because it is open, which means that it interacts with the environment. In these cases, we have to ask for the help of a mass equation. There are a lot of different mass equations, and the best known one is probably the Lindblad mass equation, which is given by the formulation here. So the Li is here is the jump operators. For example, it can be A or A dagger, and the gamma I here is the rate. Okay. So there are a few things I would like to mention about this Lindblad mass equation. First, its derivation usually requires assumptions like Markovian entity. Second, it requires d squared minus 1 many terms to describe its dynamics. So it's quadratically many. The third is that the description is not exact, though it is a very good approximation in the Markovian regime. So in the following, I will come up with a new mass equation, which is originated from an attempt to generalizing our aforementioned quantum state driving techniques into the non-unitary regime. So this new mass equation has a name, which I call it the probabilistic unitary mass equation. So this mass equation has a few features. First, it involves only unitary operators. So essentially, it is a Lindblad mass equation in the unitary form. Second is that it only involves d minus 1 many terms. So it's only linearly many as compared to quadratically many. The third is that the Qi here also denotes rate, but a little bit different from the gamma I because it has probabilistic interpretation. So before we go into more details of those mass equation, let me first show how we can derive this mass equation briefly. And actually, such derivation can just be done by an answer. The answer is this. The continuous dynamics of any finite dimensional open quantum system can be regarded as the combining effects of probabilistic combination of unitary operators plus a time-dependent Hamiltonian. Mathematically, we can formulate the answers in this way. So what this equation means is that with probability Qi dt, our quantum state rho t will be subject to a unitary transformation uit. And with probability 1 minus the summation of Qi dt, the quantum state will evolve according to its own Hamiltonian, which here is characterized by this infinitesimal form of unitary operators, ut dt. Then, by making use of tail expansion and also limit definition, we can readily obtain this probabilistic unitary mass equation. But so far, the explicit expression of h, q, and u are undeterminate. So in the following, I will briefly introduce how we can derive the explicit expression of H, Q, and U. And actually, the derivation can be completed in only 2 steps. The first step is that we start from the answers and try to first derive a mass equation for the diagonalized density matrices. So for example, we can denote our quantum state at the moment t by rho dt, which is diagonalized, and quantum state at t plus dt as this. So the eigenvalues for rho dt is p1, p2, p3, and so on. And the eigenvalues for rho t plus dt is p1 plus f1 dt, p2 plus f2 dt, and so on. And we assume in these simplified cases that the system's only Hamiltonian is 0, okay, so that we would have this for simplicity. And then we only need to find a set of unitary operators U so that we satisfy these answers. So because the UT-DT term is identity, so it contribute nothing, right? And here I claim that such a set of unitary operators U can be realized by real Y operators. And here I give example for the 4-dimensional real Y operators. And you can identify a pattern, right? There's 1, 1, 2 1s, and 3 1s. So it's a very easy pattern to identify with. And then with the help of those real Y operators, we can readily to write down and diagonalized density matrices, which is in this expression. So the effect of those unitary operators, the UI, is that they rotate the eigenvalues of rho d t cyclically, such that if initially we have the eigenvalues like p1, p2, p3, p4, then after applying the UI, we would have the new eigenvalues as p4, 1, 2, 3, or 3, 4, 1, 2, or 2, 3, 4, 1. So after plugging all of the real Y operators into the equation, we would obtain a system of equation which can be cast into this matrix product form, and from which we can solve for the Q here. Okay. So once we obtain the diagonalized density matrices, next step is that we establish an explicit correspondence between rho dot and the rho d dot, and the rho d, okay, which is given by the formula here. And finally, we just plug in the results, the rho d and the rho d dot, back into the equation here, and we are done. Okay. So to summarize, we can find that the Hamiltonian is such that it needs to satisfy a series of Schrödinger equation. Okay. And the psi I here is the instantaneous eigenvectors of rho. So what the requirement really says is that the Hamiltonian must be able to drive all of the instantaneous eigenvectors, right? And actually, this Hamiltonian has just been solved in our section 1 part, the quantum state driving part, because we've solved for the Hamiltonian that can drive quantum state along arbitrary trajectories in the mixed cases. Okay. And here, the curved U is given by the formula here, where the shadow U is the matrices that diagonalize rho, and the middle U here is the ith real Y operators. Okay. So there are a few features regarding this new formalism. First, it is exact under all cases, whether Markovian or non-Markovian. Okay. Second, it only has linearly many terms instead of quadratic number, resulting in a quadratic advantage in simulations. Third, it features unitary operators only, meaning that physical implementations would require only unitary resources, which is nice. The fourth is that the sign of the rate Qi clearly indicates the direction of information flow, since the Qi dt here denotes probability, so it has a clear physical interpretation. And finally, such a mass equation result in a natural quantum simulation control scheme, basically we can probabilistically apply the UI onto a rho with a probability Qi dt in a time interval t plus dt, so as to drive rho t along designed non-unitary trajectories. Okay. We can also generalize the formalism to infinite dimensional Hilbert space case, which basically we need to replace the d minus 1 here to infinity. And in these cases, the u here is no longer the while operators. Instead, it's given by this shift operator. Okay. Or we can generalize to the discontinuous dynamics. Here, if we denote this part as ki and this part as ki bar, then we are ready to drive this Caris-like representation. Okay, so this representation can describe any quantum channel, even if it is not a complete positive or even positive. Okay, so it's more general than the Caris representation of the quantum channel. Conclusion. The conclusion is that all quantum processes, whether open or closed, continuous or discontinuous, finite or infinite dimensional, are either unitary or probabilistic unitary, which namely is probabilistic combination of unitary evolutions. So here's an example. Here we studied the decay of two-level atom, which the mass equation can be written in this form. And if we assume that the initial state psi 0 equals to the excited state, then we can try to solve for the probabilistic unitary form of the mass equation, which is given by the equation here. And we must know that this return could be negative or even singular. Okay. Such negativity and singularity does not hamper the description, but will make the quantum control and simulation schemes to break down. Okay. And there's a caveat. The probabilistic unitary mass equation is state dependent, which means that the H, Q, and the U all depend on the current state of rho. So this implies that if we, in these cases, if we start with another initial state, the probabilistic unitary mass equation will in general be different. So instead of like the Limberland mass equation, which with one equation, we can describe all kinds of dynamics. For the probabilistic unitary mass equation, we have to describe the quantum process on an event by event basis. So thank you. And questions?
Yeah, thank you. This was really cool. I didn't totally follow in the part on the measurement collapse formalism. I wonder if you could explain again where the stochasticity comes from. I didn't quite follow that part.
Okay. Let me see. So you mean the plot here, or I think here,
yes.
right?
Yes, well, how it becomes stochastic, yes.
Yeah, so basically it's like this. If we zoom in terms of time of the projective measurement, then the process will be continuous. And our measurement devices would produce a series of readouts, RT. So the RT is a stochastic readout. It's random, and its value is between minus infinity and plus infinity. Now suppose that for a specific data, we obtain some value, say RT. And then the value RT would have a back action on the quantum state we are measuring, which means that when we obtain RT, then simultaneously the quantum state here would be pushed a little bit up or a little bit down on the arc. And when we accumulate a lot of consistent value of RT, so say we've obtained a lot of RT equals to 1, then it means that the quantum state is in the eigenstate psi I. 1 or similarity for 0. Is that clear for you?
Is there a way I can get an intuition for like the physical origin of RT? Like, what does it represent physically?
Well, it represents the readout from the measurement devices, which is like the signals reading directly from measurement devices.
Okay.
Yeah.
Thank you.
Any other questions?
Leo, I was like, can you go to your last slide where you compared like the decay of two-level system using Lindblad master equation,
Okay.
and using your unitary probabilistic unitary method. So what is the difference between the two master equations? Because I see them with like different. So you say the first one, rho dot t, I know that is from the Lindblad master equation, the first expression. You're saying the second one comes from the probabilistic unitary form, but you write one in sigma plus sigma minus and the other one in sigma x. So I was having a difficult time comparing those two. I mean, when the two becomes, can you find a situation when the two become identical?
I mean, for this specific process, like the decay of two-level atom, they are identical. Basically, it means that they describe the same physical processes. But mathematically, the sigma x is a unitary operator, right? So that's one thing. Another thing is that different from the capital gamma, which has no explicit physical imputation, the coefficient in these cases do have explicit physical imputation, which basically means that this term times dt is the probability that the sigma x is applied to the rho t. Yeah.
Okay. Did you try using this formalism also to a continuously measured two-level system, or like did you try comparing it to quantum Fokker-Planck master equation?
Yes, I did some calculation on the condition measurement part, but I didn't show it here. Yeah.
Okay.
The result is similar. Basically, it had for two-level systems, if the density matrix is diagonalized, then we would always have sigma x, and the only difference is the rate here. Yeah.
Right.
Thank you.
I have a quick question. So when you're talking about comparing doing simulations with the Lindblad equation to doing simulations with this formalism, you said that instead of having d squared operators, you're going to have d minus 1.
Yes.
So there's a saving in memory space there, but since all those operators are time dependent, the number of parameters that you have to update at each step is larger. So I was wondering, what's the trade-off between time and space complexity here? Are you trading space memory complexity for additional time complexity in general? Is that what's going on?
Yeah, that's a very good question. Yeah, and I haven't been thinking about this before. Yeah, and I think yes, it's worthwhile to really compare the complexity of two approach in more details, like considering into the fact that the U and the Q here could be time dependent. Yeah, I think that's next question, and I will study it further and see. Yeah. Thank you.
Okay.
Do you have any question in the Zoom? Okay, if not, let's thank Leo again.
Okay, thank you.
It was a really nice talk.